Hi, everyone. My name is Alyssa Pierson. I'm an assistant professor with mechanical engineering, and I'm here to talk about my semi-cooperative robot teams. So in general, I look at problems where we need to coordinate multi-agent systems. And I say multi-agent, meaning systems that might involve robots, systems that might involve humans, or systems that might involve animals. And as we think about the different ways we design the teams and the different applications that we look at, the type of interactions within the team and the type of interactions within the environment matter a lot. And the approaches that we need for things like warehouse robots where humans are not allowed, where the environment is very simple and the team dynamics are very simple, vary widely to applications in things like robotic herding, agricultural monitoring with drones, or even the grand challenge of self-driving vehicles. And so I look a lot at how we can think about the different interactions of the teams to coordinate these different multi-agent systems. And specifically, a lot of questions I like to ask are things like, how do we design teams that have performance variations among the robots? What happens if not every robot is as good as every other robot? How do we handle uncertainty? How do we handle non-cooperative teammates, so teammates that just aren't aligned with our goals? And even more challenging, how do we encounter human teammates? And across this, we end up with a spectrum of cooperation where we go from robots that are all cooperative, equally performing, all the way to malicious agents. And depending on that level of cooperation, we're going to have fundamentally different control policies. So I like to call this engineering group autonomy. And the way I accomplish this in my different research goals, I'm also team no movies on these slides, so I'll talk through a few photos. So a lot of this is looking at different geometric methods. So if we have a team of robots, can we divide the environment up into smaller pieces and distribute and decentralize some of those decisions based on different cells that the robots have? We can then combine this with different techniques in controls and game theory. So thinking about how robots not only decide actions, but also the beliefs they have about the other agents. So if we have a really selfish agent that just wants to prioritize its own actions, how do other agents adapt and compare to that? As well as different inspirations for dynamic interactions. And some work I've looked at is taking things like social value orientation, which is a concept from behavioral psychology, which looks at how humans are inclined to cooperate with one another, from things like taking altruistic actions where you're sacrificing some reward for the betterment of somebody else, through egoistic and competitive types of behaviors. And we can apply those different techniques to better model how autonomous vehicles and humans can interact at different intersections, and use some of that modeling for our robots to better predict what humans might do in these different games, as well as take those human-like models and apply them back to our robot team. So that way we can begin to design these robot teams that maybe are a little bit easier to understand or more intuitive to understand by the human teammates. And then quickly, what does my research look like on a day-to-day basis? It is a lot of math, which I won't include here, as well as playing with small-scale robots that are meant to represent things. So we don't, unfortunately, get to play with lots and lots of large vehicles, but we can introduce tiny vehicles and quad rotors in different domains in our wonderful motion capture space to illustrate these different research problems. And so thank you, and I look forward to talking to everyone further at the reception.